Welcome back. In today's lecture, we will delve into the basic concepts and methods of univariate analytics. Univariate analytics is a technique used to analyze a single variable within a dataset. It is employed when there is only one variable or when multiple variables are being analyzed individually within a dataset. This type of analysis is essential for gaining a fundamental understanding of the data's key characteristics. Univariate analytics serves as a foundational analytical technique, laying the groundwork for other methods like bivariate analysis and multivariate analysis, highlighting its importance in the field of data analysis. Let's see the table which shows the student's score of statistics. This data contains data of 50 students, so we can say that this data has 50 observations. Because of the space constraint, this form of table cannot display all of the students and their scores. And even if we can display all the 50 students, it is not very easy for us to see the whole picture of the students' performance from this table. So, we need some more efficient way of summarizing and displaying data. One way to do it is by using a frequency table. A frequency table is a table which divides the data into some classes by a certain width of the variable values and displays the number of observations for each class. This column is called frequency. Frequency represents the number of observations included in each class. So, in this example, the frequency of the class with a score of 40 to 60 is 17. A class represents intervals with which frequencies are counted. Here, a class is an interval which divides the score by every 20 points. The first class contains students whose score is greater or equal to 0 and lower than 20. Similarly, the second class contains students whose score is higher or equal to 20 and lower than 40. A frequency table usually arranges the class by ascending order with corresponding frequencies of observations. Class value is the representative value of each class, and it is the center value of each class. We can get class value by adding the lower limit and the upper limit and dividing the sum by 2. So, we can get a class value of 40 to 60 class by 60 plus 40 divided by 2. So, it is 50. The distance between the lower limits of consecutive classes is called class width. Here, it is 80 minus 60. So, it is 20. The relative frequency is calculated for each class. It is the proportion of the number of observations in the class to the total number of observations included in the dataset. We can calculate the relative frequency by dividing the frequency of each class by the total number of observations included in the dataset. When we use a sample dataset, the number of observations in a sample is called sample size. Let's see this class as an example. Since the total number of students is 50, the relative frequency of this class is calculated by dividing 17 by 50. So, it is 0.34. The cumulative relative frequency is the sum of the relative frequency of that class and all previous classes. Let's see the cumulative relative frequency of this class between 40 and 60. It is 0.08 plus 0.16 plus 0.34. So, the cumulative relative frequency is 0.58. The cumulative relative frequency of the lowest class equals the relative frequency of the class because it has no previous classes. We can get a summary of data by summary statistics. Summary statistics is a summary of observations. Specifically, summary statistics is used to summarize observations by identifying central tendency, variability, shape, and dependence. Central tendency represents a central value of a variable. Variability is the degree to which the value of a variable spread out. A shape is the shape of the data distribution. Dependence refers to interdependence between two variables, such as correlations. Central tendency is a single value that describes data in a variable by identifying the central position within the set of data. Central tendency is also called central location. Mean, also called average, is the most popular measure of central tendency. Median and mode are also measures of central tendency. A mean is an average value. It is calculated as the sum of all the variables divided by the number of observations. Generally, the mean of a variable x is written as x bar. Using the Greek capital letter sigma, we can write the formula more concisely. The notation sigma, followed by a mathematical symbol, represents the sum of all the values that the symbol can take. So, sigma x means adding up all the values x can take. So, it equals to x1 plus x2 plus x3 plus xn. The lowercase n is used to denote the number of observations. To be more precise, x bar represents the mean of a sample drawn from a population. The sample mean can be different from the population mean because the sample data is only a part of a large population. But here, we focus on the concept of sample mean because the objective of EDA is to analyze the dataset at hand, not to make inference about the whole population. As an example, let's calculate a mean of the data, which consists of 10 observations. First, calculate the sum of the 10 values, and then divide it by the number of observations, 10. So, the mean is 61.3. A mean is not always useful for representing the center of the data. Let's see these 10 observations. Now we can calculate the mean in this way. The mean is 74.3. However, you may think that 74.3 is not an appropriate value to represent the center because only two observations are above 74.3. The mean value of 74.3 does not seem to properly represent or summarize the dataset. This problem is caused by the existence of an extreme value in the dataset. In this case, the value of 216 significantly raises the mean value. Such an extreme number is called an outlier. In such a case, we can use the median to represent the center of the data. The median is the middle number when we sort the data in ascending or descending order. Suppose we have a data of 3, 2, 9, 4, and 11. To find the median, first sort the data in ascending order. There are 5 observations here. So, the middle number is the third number. It is 4. So, 4 is the median of this data. But what should we do if the data consists of an even number of observations? Let's look at a dataset with 10 observations that we saw in the previous slide. This is a sorted data. Since this dataset consists of an even number of observations, there is no actual middle number. When we use a dataset with an even number of observations, the median is the average of the middle two values. Here, the middle two numbers are 58 and 61. So, the median is 58 plus 61 divided by 2. So, it is 59.5. As we saw in the previous slide, the mean of this dataset is 74.3, and the median is 59.5. There is a big difference between the mean and the median. But as we can see in this plot, the median is the better value for representing the all data in this dataset. A median can cope with the influence of outliers. So, it is often used in dataset that contains outliers. And since it is the middle number of the dataset, usually about half of the observations are larger than it, and about half are smaller than median. When two or more datasets have the same median, it does not necessarily mean that they have similar distributions. Let's see these two sorted datasets. For both datasets, the median is 4. However, if we create the dot plots, we can easily see that the distribution of the data in these two datasets is widely different. The mode is the value that appears most often in a dataset. For example, in this dataset, the most frequent value is 3, so the mode is 3. By definition, the mode is the most frequent value in the dataset, but some dataset has 2 or more modes. For example, in this dataset, the most frequent value are 1 and 5. So there are 2 modes, 1 and 5. On the other hand, this dataset does not have a mode. All values appear only one time, and there are no most frequent values. While we cannot compute mean and median for categorical data, we can use the mode for categorical data also. However, central tendency is not sufficient to grasp the whole picture. Here, we have two datasets. These two datasets have same value of mean, median, and mode. So, all of the metrics of central tendency are same. However, when we create a dot plot these datasets, we can see that in dataset B, each data point is spread more widely. So, the data is characterized not only by the central tendencies, but also variability. There are some metrics to describe the data variability quantitatively. The range is defined as the difference between the maximum value and the minimum value of the dataset. So, we can compute the range by subtracting the minimum value from the maximum value. Let's look at these datasets. The largest number in dataset A is 8, and the smallest number is 1. So, the range is 8 minus 1 equals to 7. In dataset B, the largest number is 10 and the smallest is 2. So, the range is 10 minus 2 equals 8. The values of range tells us that dataset B is more widely dispersed. However, we can see a different picture. Let's look at the dot plots of these datasets. As you can see, in dataset B, data points are concentrated around the center. Contrary to the insight we get from the range values, it seems that dataset A is more widely dispersed. And this problem is caused by the fact that the range is very susceptible to outliers. In dataset B, there is an outlier. If we remove this outlier from the dataset, the range of dataset B becomes 2. So, if a dataset contains outlier, the range provides us with misleading results. Another popular metric of variability is variance. Variance is the average of the squared deviances. Deviance is the difference between the mean and the value of each observation. The more dispersed the data is, the greater the variance is. Let's see an example. This dataset consists of 5 observations, and the mean is 5. So, we can obtain deviance for each observation by subtracting 5 from each observation's value. Then, we can obtain the square deviance. Now, using the formula, we can obtain the value of variance. It is 3. Standard deviation is another metric of variability. It is the square root of variance. A weakness of variance is that, since it is a squared value, the unit of variance is not the same as that of the original value. For example, when we use a dataset of body weights, the unit of original value and its average are kilogram. But the unit of its variance is not a kilogram. It is a squared value of a kilogram. So, we cannot compare the value of variance and that of the mean. By the same reason, we cannot add up mean and variance. Moreover, since it is squared value, sometimes it is not easy for us to get an intuitive understanding. In particular, when the variable's value is large, it is hard to make sense of the variability. By using the square root of the variance, we can revert the unit. The square root of the variance is called a standard deviation. As with the variance, the more dispersed the data is, the larger the standard deviation is. But since it is a square root of the variance, a standard deviation has the same unit as the original value. We can compare the value and make meaningful addition and subtraction between the standard deviation and the variable's original value. Know that, not much as a range, both variance and standard deviations are also susceptible to outliers. Interquartile range, often called IQR for short, is another measure of variability. IQR is the range of the middle half of the distribution. To understand the interquartile range, first, we need to know the construct of quartile. A quartile is a point that divides the sorted data in 4 equal sizes. Commonly, from the smallest, quartiles are called the first quartile, the second quartile, and the third quartile. The second quartile is equal to the median. The first quartile is the median of the smaller half, and the third quartile is the median of the larger half. An IQR is the difference between the third quartile and the first quartile. IQR represents the middle 50% of values included in the data. IQR does not show the whole range of a variable, but it has a strength in that it is not susceptible to outliers. Let's look at an example. Here's a small dataset which consists of 9 observations. The total number of observations is an odd number. The data are sorted from the smallest to the largest. When the total number of observations is an odd number, the lower half is those to the left of the median, and the upper half is those to the right of the median. Since the number of observations is an odd number, there is an exact center, so it is 5. So, the lower half is observations, the value of which is lower than 5. The first quartile is the median of the lower half. The number of observations is 4, an even number. So, there is no exact center. So, the median is the average of the middle two values. It is 2 plus 4 divided by 2. So, it is 3. So, the first quartile is 3. Next, let's identify the third quartile. The third quartile is the median of the upper half. The number of observations is 4, an even number. So, there's no exact center. So, the median is the average of the middle two values. It is 7 plus 9 divided by 2. So, it is 8. So, the third quartile is 8. The IQR is the difference between the first quartile and the third quartile, so it is 5. Let's look at another example. Here's a dataset which consists of 10 observations. Thus, the total number of observations is an even number. The data are sorted from the smallest to the largest. We can divide the data into the lower half and the upper half, so that each contains the same number of observations. Next, let's identify the first quartile. The first quartile is the median of the lower half. The number of observations is 5, an odd number. So there is an exact center, 4. It is the median of the lower half, and it is the first quartile. In the same way, we can identify the third quartile. It is 8. So, since the IQR is the difference between the first quartile and the third quartile, it is 8 minus 4. So, it is 4.